Picture this. You're staring up at the night sky, lost in the endless sea of stars, when suddenly your radio telescope picks up a signal. Not just any signal, but something strange, something unexpected, something that shouldn't be there. A pulse of energy, a whisper from the cosmos that defies explanation. This isn't science fiction. This is real. For decades, astronomers have been catching these mysterious bursts, radio waves, laser-like beams, even patterns that seem almost deliberate. And every single one of them raises the same spine-tingling question. What or who is out there? The universe is unimaginably vast. Billions of galaxies, each with billions of stars, stretch farther than our minds can comprehend. Yet amid all that silence, all that emptiness, we keep hearing these echoes. Some last mere milliseconds, vanishing before we can trace their origin. Others repeat, teasing us with rhythms that almost feel like a code, and the strangest part, we still don't know what's causing them. Are they cosmic accidents, colliding stars, dying black holes, or some exotic physics we haven't discovered yet? Or could they be something far more extraordinary? Imagine the possibilities, signals engineered by civilizations thousands, even millions of years ahead of us, reaching across the void just to see if someone's listening. Today, we're diving deep into 25 of the most baffling signals ever detected. From the infamous WOW signal, a burst so powerful it left astronomers scribbling exclamation points, to the eerie, repeating flashes of fast radio bursts that seem to defy all known laws of physics. We'll explore the theories, the controversies, and the moments scientists were left utterly speechless. This isn't just a list, it's a journey to the edge of what we understand, where every signal is a clue, and every mystery pulls us deeper into the greatest question of all: are we alone? So buckle up. By the time we're done, you'll never look at the night sky the same way again. It started as just another routine night at Ohio State University's Big Ear Radio Telescope. August 15, 1977, the kind of quiet evening where nothing ever really happened. Astronomer Jerry Amon was scanning the skies for signs of extraterrestrial transmissions, not expecting much, just part of a long-running project called the Search for Extraterrestrial Intelligence. Then at 10:16 p.m., the equipment picked up something extraordinary, a burst of radio waves so intense, so unexpected, that when Amon saw the data print out days later, he circled the alphanumeric sequence in red pen and wrote a single word next to it: WOW. The signal lasted 72 seconds, blasting in at roughly 50 times louder than the background noise of space. It came from the direction of the constellation Sagittarius, near a star group called Chi Sagittarii, and matched almost exactly what scientists predicted an alien transmission might look like: narrow-band, powerful, and seemingly artificial. But here's what still baffles researchers: it never repeated. Despite decades of follow-up scans with more sensitive equipment, no one has ever heard it again. So where did it come from? The leading natural explanation suggests it could have been a hydrogen cloud, a comet, or some rare cosmic event we don't fully understand yet. But skeptics point out the signal was too clean, too precise. Comets don't emit narrowband radio waves like that, and if it was aliens, why wouldn't they transmit more than once? Some theorists even propose it was a one-time beacon, a cosmic hello from a civilization that's long gone, or a signal intentionally directed at us before vanishing into the void. The WOW signal remains the closest thing we've ever had to potential proof we're not alone, and yet it's also a perfect example of how maddening these cosmic mysteries can be. One fleeting moment of excitement followed by 40+ years of silence. If it was a message, we missed our chance to reply. If it was nature, it's a phenomenon we still can't explain. Either way, that red-inked WOW on Amon's printout still echoes through astronomy as a reminder. The universe is full of surprises, and we've barely begun to listen. Decades after that iconic red pen circled the data, the WOW signal still refuses to be neatly explained away. Modern astronomy has thrown every tool we have at this mystery: advanced radio telescopes, AI-powered signal analysis, even crowdsourced research. And yet, the deeper we dig, the more intriguing it becomes. In 2017, a team proposed a provocative new theory. Maybe it wasn't aliens at all, but a pair of passing comets, 266P and 335P, releasing hydrogen clouds that briefly amplified radio noise as they drifted through Sagittarius. At first, it seemed like the perfect answer, until other scientists crunched the numbers. Comets simply don't emit signals that strong or that focused. The math didn't line up, leaving the comet hypothesis floating in space like debris from a failed theory. Then there's the interstellar scintillation angle, the idea that distant cosmic plasma could have warped and magnified a weaker signal, like light bending through a funhouse mirror. But here's the catch: for that to work, the original source would still need to be something extraordinarily powerful. So even if it's true, we're back to square one. What created that initial burst? What keeps astronomers up at night, though, isn't just the signal itself, it's the silence that followed. Imagine shouting into a canyon and hearing one crystal-clear echo, then nothing but wind for 40 years. That's the torment of the WOW signal. If it was natural, why haven't we detected anything like it since? And if it was artificial, why wouldn't whoever sent it try again? Some researchers whisper about Benford beacons, a theoretical alien strategy of sending short, targeted signals to conserve energy, like cosmic flare guns shot randomly into the dark. Others wonder if we missed our window entirely, that the signal was a fleeting blip from a civilization that's now extinct. The most fascinating part: this isn't just about one 72-second anomaly. The WOW signal taught us how to listen. It inspired upgrades to SETI technology, reshaped how we filter out interference, and even influenced protocols for verifying potential alien contact. Every strange ping we detect now gets compared to that 1977 enigma, the gold standard of cosmic mysteries. And that's why, even today, when a new signal crackles through the void, someone inevitably asks, could this be the next WOW? While the WOW signal vanished without a trace, some cosmic broadcasts refused to stay silent. Enter FRB 121102, the first fast radio burst ever caught repeating its performance. Discovered in 2012 by the Arecibo Observatory in Puerto Rico, this wasn't just another blip in the static. It was a game-changer. Fast radio bursts, FRBs for short, are among the universe's most energetic mysteries. Lasting mere milliseconds, they pack the energy of 500 million suns. Most vanish instantly, never to be heard again. But FRB 121102. It played on a loop. Over months of observation, it flared again and again from the same patch of sky, a staggering 3 billion light-years away. Suddenly, astronomers had a pattern to study, a rhythm to decode. So what's behind these cosmic drumbeats? The leading suspect, magnetars. Imagine a neutron star, the collapsed core of a dead star spinning at dizzying speeds, wrapped in a magnetic field 1 trillion times stronger than Earth. When these monsters quake or snap, they could unleash bursts of radio waves intense enough to cross the universe. Supporting this theory, in 2020, astronomers traced another repeating FRB to a magnetar in our own galaxy. Case closed, not quite, because here's the twist: FRB 121102's signals aren't just repeating, they're erratic. Sometimes they cluster in frantic, minute-long storms. Other times they fall silent for months. Even stranger, their polarization suggests they've traveled through an extreme magnetic environment, like the vicinity of a black hole. Could this be a magnetar orbiting a supermassive black hole, its bursts warped by gravitational forces, or is there something even more exotic at play? Then there's the elephant in the room. Could these be artificial? some researchers, admittedly on the fringe, point to the burst's precise millisecond durations and suggest they might be signatures of alien propulsion systems. The idea, a civilization could be using focused radio beams to push light sails across interstellar distances, with each burst being a cosmic push. It's a wild theory, but in the absence of definitive natural explanations, even the improbable deserves a glance. What makes FRB 121102 so pivotal isn't just its repetition, it's the door it kicked open. Before this, FRBs were dismissed as one-off glitches. Now we know some are persistent, trackable, begging to be understood. Every new burst we detect adds another piece to the puzzle, another clue in the hunt to answer one of astronomy's biggest questions. Is the universe shouting at us, or are we just hearing echoes of its natural chaos? Either way, FRB 121102 taught us to keep listening, because sometimes the cosmos repeats itself, and when it does, we'd better be ready. What makes FRB 121102 truly baffling isn't just that it repeats, it's how it refuses to follow any predictable script. Most cosmic phenomena operate like clockwork. Pulsars tick with metronomic precision, supernova flare and fade on schedule. But this burst, it's the universe's erratic drummer playing when it pleases, daring us to decode its rhythm. Take its active periods. For weeks, it might fire off clusters of bursts, rapid fire like a cosmic machine gun. Then silence. Months could pass without a whisper, as if it's teasing astronomers before roaring back to life. This irregularity shreds conventional explanations. Magnetars, the usual suspects for FRBs, typically have rotation periods measured in seconds. So why would their radio bursts arrive in chaotic, unpredictable sprays? One theory suggests the bursts might be tangled up in an asteroid belt or a dense debris field around the magnetar, with chunks of rock occasionally triggering or blocking emissions. Then there's the polarization data, another curveball. When scientists analyzed the waves, they found them twisted into tight corkscrews, a sign they'd traveled through an incredibly powerful magnetic field. Picture a flashlight beam passing through a swirling storm of magnetized plasma. The fact that these distortions persist across billions of light years implies the signal source isn't just a lone magnetar. It's likely nested in an extreme environment, like the accretion disk of a supermassive black hole. Imagine a neutron star caught in the gravitational whirlpool of a black hole, its magnetic field stretched and warped like taffy. Every burst it emits would carry the scars of that violent relationship. But here's where it gets even stranger. Some bursts from 121102 arrive slightly offset in frequency, as if they've taken detours through different pockets of space. It's as though the signal is being lensed, bent by invisible cosmic structures on its way to us. This has led to wild speculation. Could these bursts be artificial, intentionally scattered to avoid detection? Or are we witnessing natural astrophysics so bizarre it bends our current models? The most unsettling possibility, we might be hearing echoes of a dying civilization. If an advanced species built a beacon powered by a magnetar or black hole, its signals could exhibit this exact kind of erratic, polarized behavior. Of course, that's the least likely scenario, but in science, even the fringe ideas deserve consideration when the data refuses to cooperate. What 121102 has taught us is humbling. For all our technology, the universe still holds phenomena that defy categorization. It's not just a puzzle, it's a mirror reflecting how much we have yet to learn. Every time this burst repeats, it's not just sending radio waves, it's asking us a question. How well do we really understand the cosmos? And so far, we're still scrambling for an answer. Before FRB 121102 taught us some bursts repeat, there was the one that started it all, a cosmic lightning strike so brief, most astronomers almost missed it entirely. The year was 2007, and astrophysicist Duncan Lorimer was sifting through old data from Australia's Parkes radio telescope when he stumbled on a blip that defied explanation. Lasting just 5 milliseconds, it packed the energy of 500 million suns. No supernova, no pulsar, no known phenomenon could explain it. This was the Lorimer Burst, later dubbed FRB 010724, a flash so bright it outshone entire galaxies, then vanished without a trace. Unlike the repeating bursts we discover later, this one was a hit and run. By the time anyone noticed it, the signal was already 6 years old, buried in tapes from 1998. That delay became its defining mystery. Without real-time detection, tracing its origin was like trying to find a single lit match in a forest after the flame had burned out. The numbers alone were staggering. The burst's dispersion measure how much its waves stretched as they traveled through space suggested it came from 3 billion light-years away. That meant whatever produced it had to be catastrophically powerful. A neutron star collapsing into a black hole, a cosmic string snapping, theories erupted, but the lack of a repeat performance made testing them nearly impossible. Then came another wrinkle. For years, some skeptics argued it might not even be cosmic. Parkes sits in sheep-grazing country, and radio interference from earthly sources, microwave ovens, satellites, even farm equipment had fooled astronomers before. But the Lorimer Burst's fingerprint was unmistakable. Its frequencies descended in a perfect slope, a telltale sign of waves traveling through interstellar plasma. This wasn't a malfunctioning kitchen appliance. This was something from deep space. What makes the Lorimer Burst so pivotal isn't just its power, it's the door it kicked open. Before this, nobody imagined millisecond radio flashes could carry such energy. Its discovery forced astronomers to rewrite their playbooks, spawning entire research programs dedicated to hunting these elusive signals. And while we've since found hundreds more FRBs, the original remains a benchmark. A reminder that sometimes the most universe-shattering discoveries begin with a flicker, one so fast you'd blink and miss it. The discovery of the Lorimer Burst didn't just add another mystery to astronomy's growing list, it rewrote the rulebook for how we scan the skies. Before that 5-millisecond blip, nobody was actively hunting for ultra-fast cosmic flashes. But the moment scientists realized what they'd found, a global race began to catch more of these fleeting signals in real time. The challenge, FRBs are cosmic, will owe the wisps here one instant, gone the next. Traditional telescopes weren't built to capture split-second anomalies buried in terabytes of static, so astronomers got creative. Enter the next generation of radio arrays. Facilities like CHIME in Canada, a sprawling network of cylindrical antennas resembling half-pipes, were designed to scan vast swaths of sky simultaneously, snapping cosmic snapshots every millisecond. Unlike single-dish telescopes, which focus on narrow patches of space, CHIME acts like a wide-angle lens, catching bursts that older instruments would have missed. The payoff was immediate. In just its first year of operation, CHIME detected over 500 new FRBs, including dozens of repeaters like 121102. Suddenly, what seemed like rare flukes were everywhere, hinting that the universe might be crackling with these signals, if only we had the tools to hear them. But hardware was only half the battle. Analyzing this flood of data required something equally revolutionary: machine learning. Sorting through billions of radio waves for milliseconds-long anomalies is like finding needles in a cosmic haystack. Algorithms trained to recognize FRB signatures now sift through the noise, flagging potential bursts faster than any human team could. In one famous case, an AI at Parkes spotted an FRB so faint researchers initially dismissed it as interference until the machine pointed out its telltale dispersion pattern. Perhaps the most surprising twist: the more FRBs we find, the weirder they get. Some arrive with lower frequencies, suggesting they've traveled through denser regions of space. Others show up in bizarre locations, like one that seemed to emanate from inside our own galaxy, only to later be traced to a magnetar's outburst. Then there's the sad trombone effect, where bursts descend in pitch like a comedic slide whistle, a quirk caused by plasma scattering their waves. Each peculiarity adds another piece to the puzzle, forcing theorists back to their chalkboards. What began as a solitary blip on a decades-old tape has become one of astronomy's most dynamic frontiers. Today, networks of telescopes sync up worldwide, alerting each other within seconds when an FRB strikes, swiveling to triangulate its origin. There's even a citizen science project Einstein at home where volunteers donate computer time to scour archival data for missed bursts. The Lorimer Burst didn't just spark curiosity, it ignited a movement, and as our tools grow sharper, one thing's certain: the cosmos still has plenty of surprises left to shout about. We just have to keep listening. In the early 2000s, as astronomers sifted through years of SETI data, one signal stood out like a sore thumb: SHB02 plus 14a. Detected not once, not twice, but 3 times in 2003, this wasn't some random cosmic noise. It pulsed at 1420 MHz, a frequency with eerie significance. That's where neutral hydrogen, the most common element in the universe, naturally emits energy. In other words, it's the cosmic equivalent of shouting on a crowded channel where everyone's already listening. What made SHB02 plus 14 so tantalizing was its drift, the way its frequency slid slightly over time. This wasn't static interference from Earth. The shift matched the rotation of a planet, as if the source was anchored to a spinning world and the origin point. A patch of sky near the Pisces and Aries constellations, where no known stars or planets should have been broadcasting. SETI researchers rushed to check for glitches, but the signal's behavior was too precise, too deliberate. It looked, for all intents and purposes, like a beacon, but here's where it gets complicated. The signal was weak, barely peaking above the noise floor, and despite multiple attempts, nobody could pin down its exact location. Some argued it might have been atmospheric distortion or a glitch in the Arecibo telescope's hardware. Others pointed out that the frequency, while intriguing, could also overlap with human-made signals, military radar, or satellite transmissions bouncing off the ionosphere. The more scientists scrutinized it, the murkier it became. Yet SHB02 plus 14 refuses to fade into obscurity. Why? Because of what it represents: the razor-thin line between discovery and dead end in the search for extraterrestrial intelligence. It's the kind of signal that fits just enough criteria to spark excitement but dodges confirmation like a cosmic will-o'-the-wisp. Some researchers still hold out hope it was a fleeting hello from a civilization far older than ours, a transmission that flickered out before we could properly answer. Others insist it's a cautionary tale, a reminder that the universe is full of natural phenomena we've yet to understand. One thing's certain: until we catch another signal like it, SHB02 plus 14 will linger in the annals of astronomy as both a tantalizing maybe and a frustrating mystery. It's the radio equivalent of seeing a shadow move in the dark, just enough to make you wonder, but never enough to be sure. The debate over SHB02 plus 14 wasn't just a scientific curiosity. It became a litmus test for how SETI operates in an era of cosmic ambiguity. When the signal first pinged on their radar, researchers scrambled to apply the organization's strict verification protocols. Known as the SETI 3-step, this process involves cross-checking a signal across multiple telescopes, ruling out terrestrial interference and confirming its celestial origin. But SHB02 plus 14 slipped through the cracks of this framework like smoke. It appeared sporadically, never long enough for simultaneous detection by a second facility. Its faintness made it impossible to distinguish conclusively from background static. And that tantalizing frequency drift, it could have been caused by atmospheric refraction or even a glitch in the telescope's receiver. This uncertainty split the SETI community into 2 camps. On one side, skeptics argued the signal was a textbook example of Percival's curse. a term coined after Percival Lowell mistakenly mapped canals on Mars, seeing patterns where none existed. They pointed to previous false alarms like the famous LGM-1 signal that turned out to be a pulsar, not little green men. To them, SETI-02 plus 14 was just another cosmic mirage, a quirk of radio noise masquerading as significance. But the optimists fired back with a compelling counter. What if we're too quick to dismiss? SETI astronomer Seth Shostak noted that an actual alien transmission might not behave like we'd expect. Advanced civilizations could use burst messaging or frequency hopping to conserve energy, making their signals inherently elusive. The very irregularity of SETI-02 plus 14a, he argued, might be its most alien feature, a deliberate design to avoid detection by primitive listeners like us. The controversy spilled beyond academic circles when a leaked memo revealed that the signal's coordinates aligned roughly with a then undiscovered exoplanet system. Conspiracy theorists pounced while astronomers groaned. The truth was far less dramatic, the overlap was coincidental, and subsequent studies found no planets in the signal's path. But the episode exposed a deeper tension in SETI mission. In a universe awash with natural radio noise, how do you distinguish a hello from a hiccup? SETI-02 plus 14a's legacy isn't just about one unresolved signal. It forced SETI to refine its detection algorithms, accounting for drifting frequencies and transient bursts. It inspired new listening projects like Breakthrough Listen, which now scans millions of frequencies simultaneously. And perhaps most importantly, it reminded us that the search for extraterrestrial intelligence isn't just about finding answers, it's about learning how to ask the right questions. Because sometimes the most profound discoveries begin with a whisper we can't quite decipher. In July 2017, astronomers at Puerto Rico's Arecibo Observatory, fresh from upgrades meant to boost its sensitivity, turned their dish toward a seemingly unremarkable red dwarf star called Ross 128. Just 11 light-years away, it was a routine target for studying stellar flares and planetary formation. But what came back wasn't routine at all. The telescope recorded a series of peculiar bursts, each lasting about 10 milliseconds, with a frequency drift that made zero sense for natural phenomena. Even stranger, the signals only appeared when they pointed at Ross 128. Shift the telescope slightly away and the static returned to normal. For a tense 72 hours, the astronomy world held its breath. Here was a signal with all the hallmarks of artificial origin, narrowband, drifting in a way that mimicked a transmitter on a rotating planet, and localized to a single star system. The internet erupted. Had we finally found proof of extraterrestrial technology? The SETI Institute scrambled their Allen telescope array to listen in, while researchers pored over every possible explanation, from stellar activity to satellite interference. Then came the twist. When astronomers revisited Ross 128 with different instruments, the signal was gone. Not just silent, vanished as if it had never existed. Digging deeper, they found the culprit: geostationary satellites, specifically transmissions from a distant orbit nearly 9,000 miles above Earth, bouncing off the ionosphere at just the right angle to mimic a signal from Ross 128's direction. The frequency drift, a side effect of the satellite's motion relative to Arecibo's position. While the answer was disappointingly terrestrial, Ross 128's brief moment in the spotlight revealed something crucial about our search for cosmic company. Even with cutting-edge tech, the universe loves to play tricks on us. Satellites we've placed in orbit can masquerade as alien broadcasts. Cosmic noise can mimic deliberate patterns. And sometimes the most tantalizing mysteries turn out to be artifacts of our own ingenuity, echoes of humanity bouncing back to us from the void. The Ross 128 signal wasn't ET calling home. But it was a stark reminder: before we can hear the universe, we must first learn to filter out our own noise. The Ross 128 incident wasn't just a dead end, it was a masterclass in cosmic humility. Every false alarm like this forces astronomers to confront the same uncomfortable truth. The universe is a noisy place, and our own backyard is the noisiest of all. Between satellite transmissions, radar echoes, and even microwave ovens leaking interference, yes, that's happened. Earth's electronic chatter creates a minefield of potential false positives. But here's the paradox: the better our telescopes get, the more of these red herrings we'll find. Take the case of perytons, a class of signals that baffled scientists for years. These brief, dispersed radio bursts seem to originate from deep space, matching many characteristics of FRBs. Then, in 2015, researchers at Parkes made an accidental discovery. The signals stopped when staff updated the observatory's microwave. Turns out, opening the microwave door mid-cycle emitted a frequency sweep eerily similar to a cosmic burst. The culprit: hungry astronomers reheating lunch, yet dismissing all anomalies as human-made risks, missing the real deal. Nature loves to impersonate technology. Pulsars, for instance, were initially nicknamed LGM-1, little green men, because their precise pulses seemed artificially engineered. The key lies in triangulation. A genuine cosmic signal will appear consistent across multiple observatories worldwide, while local interference won't, but even that's not foolproof. Atmospheric conditions can refract signals, making them appear to drift, just like SETI-02 plus 14a. What Ross 128 taught us goes beyond technology. It revealed the psychological tightrope scientists walk: too much skepticism, and we might ignore a groundbreaking discovery; too much optimism, and we risk crying wolf. The solution: a new generation of verification protocols like breakthrough listens, multi-location simultaneous observation rule. No signal gets taken seriously unless detected independently by telescopes on different continents. Perhaps the most valuable lesson is this: every false alarm sharpens our tools. The algorithms that now weed out satellite interference were trained on mistakes like Ross 128. The databases tracking human-made radio pollution, built from years of dead ends. In the end, the search for extraterrestrial signals isn't just about listening to the cosmos, it's about learning to distinguish the universe's voice from our own echo. And sometimes the silence between the noise teaches us the most. Among the hundreds of fast radio bursts we've detected, one stands out not for its power or its distance, but for its eerie punctuality. FRB 180916 doesn't just repeat, it keeps a calendar. Every 16.35 days, like clockwork, this burst, nestled in a galaxy 500 million light-years away, fires off a cluster of radio waves for roughly 4 days. Then, as if flipping a cosmic switch, it goes silent for 12. This isn't the erratic staccato of other repeating FRBs, it's a rhythmic pulse, the universe's most reliable metronome. And that predictability has astronomers both thrilled and utterly baffled. What could possibly explain such clockwork precision in the chaotic depths of space? The leading theory revolves around a binary system, a dance between two celestial objects. Picture a highly magnetized neutron star, possibly a magnetar, orbiting another massive body like a black hole or a giant star. As the magnetar swings through its orbit, its intense magnetic field might become periodically obscured or disrupted by its companion's gravity or stellar wind. During the on phase, its radio bursts could escape unimpeded. Then, as it moves behind its partner, the signals get temporarily blocked, creating that 12-day silence. It's the cosmic equivalent of a lighthouse beam disappearing behind a rotating barrier. But here's where the mystery deepens. While binary systems are common, none we've observed behave quite like this. The timing is too precise, the bursts too consistent. Some researchers speculate the magnetar's companion might be a B star, a hot, fast-spinning star surrounded by a dense disk of gas. As the magnetar plows through this disk at regular intervals, the resulting shock waves could trigger the radio bursts like cosmic Morse code. Others propose an even wilder idea. What if the 16-day cycle isn't orbital at all? What if it's the rotation period of some megastructure, an alien energy collector or beacon spinning to focus its transmissions? The implications of FRB 1809-16's rhythm extend beyond its origin. Its predictability has given astronomers something rare, a chance to prepare. Teams worldwide now sync their observations to its active windows, training arrays of telescopes on its location like paparazzi staking out a celebrity's schedule. Already, these coordinated efforts have revealed finer details, sub-millisecond structures within the bursts, subtle frequency shifts that hint at the environment they're traveling through. Each observation peels back another layer of the mystery, yet for all we've learned, the 16-day cycle raises more questions than answers. Why don't other repeating FRBs display such regularity? Is this a common phenomenon we've simply missed because most bursts are too faint or distant to track long-term? Or is FRB 1809-16 a cosmic unicorn, a rare configuration that somehow stumbled into perfect synchronization? The more we study it, the clearer it becomes. This isn't just another burst. It's a masterclass in cosmic timing, a reminder that even in the chaos of the universe, patterns lurk, waiting for us to decipher their code. That 16.35-day cadence from FRB 1809-16 isn't just a curiosity, it's a cosmic fingerprint, pressing its in-Chi swirls across everything we thought we knew about fast radio bursts. Most repeating FRBs fire off randomly, their outbursts as erratic as a toddler with a drum set. But this one, it's more like a Swiss watch buried in the debris of a supernova, ticking with precision that defies the chaos around it. So what does that kind of predictability mean for our understanding of these enigmatic signals? First, consider the sheer stability of that cycle. In astronomy, regular intervals usually point to orbital mechanics, something locked in a gravitational embrace with another massive object. But here's the catch: even in tight binary systems, small fluctuations are inevitable. Tidal forces distort orbits, stellar winds erode trajectories. Yet this FRB's rhythm is unshakable, down to the decimal. That suggests an environment of extraordinary balance, like a neutron star skating along the razor's edge of a black hole's gravitational field without slipping in. Or perhaps something even stranger, a magnetar whose magnetic axis wobbles just right every 16 days, funneling its bursts toward us like a lighthouse beam cutting through fog. Then there's the burst structure itself. Unlike the frenetic volleys of FRB 121102, the signals from 1809-16 arrive in disciplined clusters, each one a near-perfect replica of the last. This isn't the splatter of a cosmic paintball gun, it's the measured strike of a hammer on an anvil. Some theorists argue this points to a clean environment, no messy asteroid belts or plasma storms to scramble the signal. Others propose the bursts are being actively shaped, their emission funneled through some natural or unnatural aperture to keep them coherent across 500 million light-years. But the most tantalizing clue lies in what we don't hear. During those 12 days of silence, the FRB isn't just quiet, it's absent. No weaker pulses, no background static. It's as though the source gets switched off entirely. That's bizarre for celestial objects which rarely have on-off switches, unless, of course, the silence isn't a pause but a shadow. Imagine the FRB's source orbiting behind a thick curtain of gas or a companion star's fiery corona, its signals blocked as cleanly as a stage light behind a drop curtain. All these quirks have led to whispers of even wilder possibilities. Could that 16-day cycle align with something like a Dyson swarm's rotation, a megastructure harvesting energy from its star in rhythmic pulses? It's a fringe idea, sure, but the universe has surprised us before. After all, pulsars were once mistaken for alien beacons. The real lesson here: patterns in nature don't emerge without reason. And when we find one this precise, it's either a cosmic coincidence of staggering odds, or a signpost pointing to physics we've yet to dream up. For now, FRB 180916 keeps its secrets ticking across the cosmos with metronomic indifference. But with every cycle, it leaves us a little more data, another breadcrumb on the path to understanding. And in the grand puzzle of fast radio bursts, that kind of reliability isn't just helpful, it's revolutionary. Because in a universe of randomness, sometimes the most alien thing isn't the noise, it's the silence between the beats. Imagine a star that doesn't just flicker, it plummets in brightness, dimming by up to 22% at erratic intervals, as if something colossal is passing in front of it. Not a planet, not a comet, something bigger. That's the enigma of KC 8462852, better known as Tabby's star, named after astronomer Tabby, who first documented its bizarre behavior in 2015. This star, 1,200 light-years away in Cygnus, became an instant celebrity, not for what it was, but for what it wasn't doing. Normal stars dim in predictable, gentle rhythms. Tabby's star, it's more like a cosmic light switch being yanked by a poltergeist. The intrigue began with Kepler, a planet-hunting telescope. Kepler watched this star for years, recording its light like a devoted stenographer. Most stellar dips are orderly, tiny, repeating blips caused by orbiting planets. Tabby's star's dips, though, were anything but. Some lasted days, others mere hours. The most dramatic drop, a staggering 22% of its light vanishing, as if a giant shutter had snapped closed. For context, even a Jupiter-sized planet would only block about 1% of a star's light. Whatever was causing this wasn't just big, it was unlike anything we'd ever seen. Cue the alien megastructure hypothesis. Enter Jason Wright, an astronomer who floated the idea that made headlines worldwide. Could these dips be caused by a Dyson swarm, a vast network of energy collecting satellites built by an advanced civilization? The concept wasn't entirely fringe. In the 1960s, physicist Freeman Dyson theorized that a sufficiently advanced society might encase its star in solar panels to harness its power. If fragments of such a structure orbited Tabby's star, their irregular shapes and movements could explain the erratic dimming. Suddenly, a once obscure star became a battleground between skeptics and dreamers, between astrophysics and science fiction. But before we etch aliens into the cosmic record, let's talk dust. The leading natural explanation: swarms of circumstellar debris. Think colossal rings of dust and comet fragments orbiting the star in chaotic clumps. Observations from the Spitzer and Hubble telescopes revealed the star's infrared emissions fit this model. Dust absorbs visible light and re-emits it as heat, which matches the data. There's just one problem. The amount of dust required is staggering. We're talking about enough material to make entire planets, ground into fine particles and spread unevenly across vast orbits. How did it get there? One theory suggests a catastrophic planet-on-planet collision, vaporizing rocky bodies into a haze of debris. Another proposes a family of exocomets, ice and rock fragments spiraling inward from the star's frigid outer reaches, boiling as they near the heat and leaving trails of dust. Yet even these explanations strain credulity. The comet hypothesis, for instance, would require hundreds of thousands of giant comets passing in front of the star simultaneously to account for the deepest dimming events. That's an implausibly crowded neighborhood for one star. Meanwhile, the dust itself behaves oddly, seeming to dissipate and reform over time, a dynamic process we've never observed elsewhere in such extremes. Then there's the star's long-term dimming. Over the past century, archival data shows Tabby's star has faded by nearly 15% overall. No known stellar phenomenon, no cycle of sunspots, no internal hiccups explains that kind of sustained darkening. Some theorists speculate that we're witnessing the aftermath of a swallowed planet, its remains still swirling in the star's atmosphere. Others suggest an interstellar dust cloud drifting between us and the star, though no such cloud has been detected. What makes Tabby's star so mesmerizing isn't just the mystery, it's the way it forces us to stretch our imaginations. Whether it's alien megastructures or freakish cosmic dust storms, none of the proposed explanations feel entirely satisfactory. That's the beauty of anomalies. They reveal the edges of our understanding, the places where textbooks end and curiosity takes over. Every new observation, every flicker, every dip is a clue in a celestial whodunit, one that might rewrite the rules of stellar behavior or, just maybe, introduce us to something beyond our wildest dreams. For now, Tabby's star keeps its secrets, winking at us across 1,200 light years. But with every telescope trained on it, every algorithm sifting through its data, we're inching closer to answers. And in that tension between the known and the unknown, the mundane and the extraordinary, lies the heartbeat of discovery. Because sometimes the universe's greatest gift isn't solving the puzzle. It's realizing how much bigger the puzzle really is. Years after its discovery, Tabby's star still refuses to play by the rules. While most astronomical mysteries gradually yield to scrutiny, this enigmatic flicker in Cygnus only deepens its intrigue with each new observation. In 2021, the star did something unexpected. It dimmed again, but this time in ways that shattered previous patterns. Instead of the deep, jagged dips Kepler recorded, the new dimming events were shallower, more prolonged, almost as if the star itself was changing its tactics. Astronomers scrambled telescopes worldwide to catch every photon, hoping this fresh data would finally crack the case. Instead, it only added another layer to the puzzle. One of the most baffling revelations, the star's dimming isn't uniform across all wavelengths. When observed in ultraviolet light, the dips are far more pronounced than in infrared, a smoking gun suggesting the obstructing material isn't just ordinary dust. Fine cosmic dust typically scatters blue and ultraviolet light more effectively, but Tabby's star's behavior implies something stranger. A mix of particle sizes, perhaps even microscopic structures with unusual light-blocking properties. Could this be evidence of exo-asteroids pulverized into exotic fragments, or something even more unconventional? The data refuses to settle the debate. Then there's the star's long-term fading, another curveball. Archival plates from the 19th century showed Tabby's star was significantly brighter a century ago, dimming by nearly 15% since then. No known stellar life cycle explains this. Stars like Tabby's, an F-type main sequence star, should remain stable for billions of years. Yet here we are, watching one throw a tantrum on a human timescale. Some theorists suggest the star might have recently ingested a planet or a brown dwarf, its digestion process still playing out in violent atmospheric disturbances. Others propose an interstellar cloud drifting between us and the star, though no such cloud has ever been detected. But the most electrifying twist came in 2022, when a team analyzing data from the Transiting Exoplanet Survey satellite spotted something peculiar. The star's dips weren't just random, they hinted at a faint rhythmic pattern. Not the rigid clockwork of FRB 1809-16, but a loose correlation that suggested orbital influences. Could a massive planet with a chaotic debris field be stirring things up? Or was this the ghostly fingerprint of a megastructure's construction phase, its uneven silhouette rotating into view? Even the soberest astronomers admit the data leaves room for interpretation. What makes Tabby's star so endlessly fascinating isn't just the mystery, it's the way it forces us to question our assumptions. Every time we think we've pinned it down, it slips free, dangling new possibilities just out of reach. Whether it's aliens, dust, or something we haven't even dreamed up yet, this star reminds us that the universe always keeps a few cards hidden. And as long as it keeps winking at us from 1,200 light years away, we'll keep watching, measuring, and wondering what's really going on out there. In August 2015, a Russian radio telescope scanning the skies near the constellation Hercules caught something extraordinary. A 2-second radio spike so peculiar that when the news quietly leaked a year later, it sent shockwaves through the astronomy community. The signal came from HD 164595, a sun-like star 94 light-years away, and it ticked all the boxes for potential artificial origin. Clocking in around 11 gigahertz, the frequency matched what theorists predicted an advanced civilization might use for interstellar communication. Even more intriguing, the signal's strength suggested an isotropic transmitter, one blasting energy equally in all directions, would require power equivalent to 100 trillion watts. That's more energy than all of human civilization currently consumes. For a brief, electrifying moment, the possibility of contact seemed tantalizingly real. Researchers at the SETI Institute scrambled to train the Allen telescope array on HD 164595, while astronomers debated whether the signal could have been a deliberate effort to get our attention. After all, the star's similarity to our Sun made it a prime candidate for hosting life. Unlike the erratic pulses of FRBs or the murky origins of Tabby's star, this was a clean, narrowband radio burst, the kind we'd expect from a beacon rather than a cosmic accident. But the hype was short-lived. Within weeks, the signal's allure began to unravel. First, independent observatories failed to detect any repeat transmissions. Then, researchers noticed something odd: the signal's frequency aligned suspiciously close to bands used by Russian military satellites. By September, the consensus was clear. HD 164595's alien broadcast was almost certainly a false alarm, likely a stray transmission from a passing surveillance satellite or an aircraft. The SETI Institute's Seth Shostak summed it up wryly. The universe has a wicked sense of humor, dangling cosmic carrots only to yank them away. Yet the story doesn't end there. What makes this signal remarkable isn't its ultimate debunking. It's what it revealed about our search for cosmic neighbors. For one, HD 164595 exposed the messy reality of radio astronomy in the 21st century. Earth's orbital space is now so cluttered with satellites and debris that distinguishing human noise from potential alien signals grows harder every year. The signal also underscored the importance of rapid response protocols. Unlike the WOW signal, which was discovered years too late for follow-up, this detection prompted immediate scrutiny, showcasing how far SETI verification processes have come. But perhaps the most enduring lesson lies in the star itself. HD 164595 isn't just any sun-like star. It's known to host at least one Neptune-sized planet. While that world orbits too close to be habitable, its existence hints at a broader planetary system, one that might include Earth-like worlds in more temperate zones. The signal may have been a dud, but the star remains a compelling target for future study. After all, if someone out there is listening, they might not be shouting. They could be whispering, waiting for us to refine our ears. And HD 164595 reminds us that sometimes the quietest stars hold the loudest secrets. The story of HD 164595 didn't just unfold in scientific journals. It exploded across headlines worldwide, igniting a media storm that perfectly captured the tension between sober astronomy and the public's hunger for cosmic wonder. Within hours of the signal's existence leaking, tabloids blared, "Aliens finally found," while tech billionaires mused about interstellar replies. Even normally staid news anchors couldn't resist breathless speculation, framing the detection as humanity's first brush with something other. Yet behind the scenes, scientists gritted their teeth. They'd been here before. Every ambiguous signal, from the WOW to SETI 02 plus 14a, had triggered the same cycle of hype and letdown. But HD 164595 was different. This time, the frenzy reached fever pitch before the data could even be verified. The speed of misinformation was staggering. Before astronomers could coordinate follow-up observations, social media had already woven elaborate narratives, claims of mathematical patterns. In the signal, there were none. Whispers of government cover-ups debunked by open-source telescope logs, even fabricated screenshots of alien messages circulating as proof. The star's sun-like properties only fueled the fire, with armchair theorists arguing its similarity to Earth's sun made it an ideal candidate for life. Lost in the noise was a critical fact. HD 164595's single detected signal was weaker than a smartphone's GPS transmission by the time it reached Earth. If this was a beacon, it was either broken or not meant for us. Scientists found themselves trapped in a paradox. On one hand, transparency demanded sharing potential breakthroughs, even tentative ones. On the other, premature announcements risked eroding public trust when explanations proved mundane. The backlash was swift once the satellite interference theory gained traction. Conspiracy forums accused astronomers of hiding the truth, while casual observers dismissed SETI as crying wolf again. The irony: this very signal, despite its terrestrial origins, demonstrated how exquisitely sensitive our detection tools had become. The ability to spot a faint, suspicious blip across 94 light-years was itself a triumph. Yet that nuance vanished beneath sensationalism. What emerged from the chaos was a watershed moment for science communication. Major institutions, including NASA and the SETI Institute, overhauled their disclosure protocols, adopting tiered response plans that clearly distinguish between intriguing anomalies and verified discoveries. Media partnerships were forged to ensure accurate reporting, with embargo systems allowing scientists to vet findings before public release. Even the terminology shifted. Phrases like candidate signal and requiring confirmation entered mainstream lexicons, tempering expectations without dampening curiosity. HD 164595's legacy isn't just about a false alarm. It's a masterclass in how fragile the relationship between science and society can be when confronting the unknown. The public's yearning for cosmic companionship is powerful, but so is the weight of evidence. Balancing those forces, maintaining rigor while nurturing wonder, is perhaps the greatest challenge in the search for extraterrestrial intelligence. Because somewhere between reckless speculation and clinical detachment lies the truth. The universe is strange enough without inventing stories, and sometimes the most profound lesson isn't in the signal itself, but in how we choose to listen. While most repeating FRBs like 121102 and 1809 won 6 grab headlines with their rhythmic encores, there's another breed of burst that refuses to perform twice ephemeral cosmic sparks that vanish as suddenly as they appear. Enter FRB 190523, a flash of radio waves so fleeting it was nearly lost in the noise, detected by the Deep Synoptic Array in California. This burst arrived in June 2019 with all the hallmarks of a classic FRB: millisecond duration, massive energy output, and a telltale frequency sweep. But one detail set it apart: its home. Unlike earlier bursts traced to bustling star-forming galaxies, this one came from a quiet, aging galaxy 6 billion light-years away, a place where the frenetic births and deaths of stars had long since settled into cosmic middle age. That location was a game-changer. Before 1905-23, astronomers assumed FRBs were born from extreme environments, regions choked with newborn stars, magnetars, or black holes. But this burst's serene galactic neighborhood shattered those assumptions. If even a sedate galaxy could produce such an energetic signal, then whatever creates FRBs isn't tied to the fireworks of stellar youth. It hinted at a diversity of origins we're only beginning to grasp. Could these bursts arise from multiple cosmic pathways, collisions between dense stellar remnants in quiet galaxies? Or perhaps exotic physics in the halos of ancient stars? The mystery deepened when follow-up observations failed to catch a repeat. Unlike 121102's persistent encores, 1905-23 was a one-hit wonder. That rarity makes it both tantalizing and frustrating. Repeaters offer data, one-offs leave only breadcrumbs, but what crumbs they are. The burst's dispersion measure, how its waves stretched during transit, revealed it had traversed an unusually sparse patch of intergalactic space, missing the dense plasma clouds that typically distort such signals. That clean passage gave astronomers an almost pristine sample of the burst structure, revealing subtle frequency dips that might encode clues about its birthplace. The most compelling theory, a magnetar formed not from a supernova's chaos, but from the quieter merger of two white dwarfs. In this scenario, the combined mass of the dead stars would collapse directly into a neutron star without the usual stellar explosion, leaving behind a highly magnetized remnant in an otherwise peaceful galaxy. It's a cosmic sleight of hand, a violent event masquerading as serenity. FRB 1905-23's legacy isn't just about adding another entry to the FRB catalog. It's a reminder that the universe loves to defy categories. For every repeating burst with a predictable cadence, there's a one-off that upends our assumptions. And in that diversity lies a thrilling possibility. We're not just hunting for the source of a single phenomenon. We're piecing together a cosmic puzzle where every burst, whether it echoes or vanishes, rewrites the rules. FRB 1905-23 didn't just defy expectations. It rewrote the map of where we thought cosmic fireworks could ignite. Before this burst flared into view, astronomers had a neatly packaged theory. Fast radio bursts were the exclusive domain of young, rambunctious galaxies. The logic seemed sound. These stellar nurseries, brimming with newborn stars and the violent deaths of massive suns, were the perfect breeding grounds for magnetars and other extreme objects capable of generating FRBs. But 1905-23 blew that assumption to pieces. Its host galaxy was the cosmic equivalent of a retirement community, quiet, settled, with little trace of the chaotic star formation that supposedly birthed these radio bursts. This wasn't just an oddball observation, it was a paradigm shift. Imagine searching for tornadoes only in the tropics, then stumbling upon one in the Arctic. The discovery forced scientists to confront a glaring question. If FRBs could emerge from such serene environments, what did that say about their origins? Suddenly, the playbook was wide open. Maybe magnetars weren't just forged in supernova explosions. Perhaps they could arise from quieter mergers, two white dwarfs colliding in a whisper rather than a bang, their combined mass silently collapsing into a neutron star. Or maybe there were entirely new mechanisms at work, processes we hadn't even considered because we'd been looking in the wrong places. The implications ripple outward. If FRBs aren't tied to star-forming regions, their distribution across the universe could be far more widespread than we imagined. That means they might not just be cosmic anomalies. They could be ubiquitous, lurking in every type of galaxy, from the bustling metropolises of spiral arms to the sleepy outskirts of elliptical giants. And that changes how we hunt for them. No longer can we focus telescopes solely on the brightest, most active galaxies. The real answers might be hiding in the quiet corners, the places we've overlooked because they seem too ordinary to harbor such extraordinary phenomena. But here's the twist. 1905-23's host galaxy, while calm now, might not always have been so peaceful. Galaxies evolve over billions of years, and what looks like a retirement home today could have been a stellar nightclub in its youth. Some researchers speculate this burst could be a delayed echo, a magnetar born in a long-ago era of chaos, only now making its presence known. It's like finding a lit firecracker in an abandoned factory. The explosion might be happening now, but the fuse was set decades ago. What makes this burst so revolutionary isn't just the mystery it poses, it's the door it kicks open. By proving FRBs can emerge from unexpected places, 1905-23 forces us to broaden the search. No longer can we rely on simplistic models or single origin theories. The universe, it seems, has more than one way to cook up these enigmatic signals. And that's the beauty of astronomy's greatest puzzles. Just when we think we've pinned them down, they remind us how much we still have to learn. the map of FRBs just got a lot more interesting, and the uncharted territories might hold the answers we've been searching for all along. In December 2020, astronomers monitoring our closest stellar neighbor, Proxima Centauri, caught something extraordinary, a narrowband radio signal at 982 MHz, pulsing like a cosmic heartbeat from just 4.2 light-years away. Dubbed BLC-1, this wasn't random static. It was a clean, concentrated beam, drifting in frequency the way you'd expect if the source was attached to a rotating planet. For a moment, the world held its breath. Had we just intercepted a transmission from the star system next door? Proxima Centauri is no stranger to intrigue. A red dwarf smaller and cooler than our Sun, it hosts at least 2 confirmed planets, including Proxima b, a rocky world snugly nestled in the habitable zone where liquid water could theoretically exist. The idea that a civilization might thrive there, close enough to practically wave across interstellar space, sent imaginations into overdrive. The signal's characteristics only fueled the fire. Unlike the messy broadband noise of natural cosmic phenomena, BLC-1 was laser-like, confined to a tight sliver of the radio spectrum, precisely the fingerprint of artificial transmission. Even skeptics admitted this was the most compelling candidate since the WOW signal, but the euphoria was short-lived. As researchers at the Breakthrough Listen project dug deeper, inconsistencies emerged. The signal's frequency drift, while initially promising, didn't quite match Proxima Centauri's predicted motion. More damningly, when telescopes scanned the star again, the signal failed to reappear, a red flag for terrestrial interference. The final nail in the coffin, further analysis revealed BLC-1's frequency overlapped with known ranges of human-made electronics, the likely culprit. A malfunctioning satellite or ground-based equipment, its radio leakage masquerading as an interstellar hello. Yet the Proxima Centauri signal's legacy isn't just another case of boy who cried wolf. It exposed a tantalizing irony. Our search for extraterrestrial intelligence is now so advanced, we can detect our own technological noise with unprecedented sensitivity. BLC-1's false alarm underscored the growing challenge of filtering Earth's electronic cacophony from genuine cosmic whispers. It also reinforced a humbling truth: even our nearest stellar neighbor, practically a stone's throw in galactic terms, remains frustratingly silent. But silence doesn't mean surrender. If anything, BLC-1 sharpened our tools. The protocols developed to debunk it now help astronomers distinguish human-made signals faster, refining the search for the real deal. And Proxima Centauri remains a prime target. Its planets, bathed in the dim glow of their red sun, still offer some of the most promising real estate for life beyond our solar system. One day, a signal from there might not be a false alarm. Until then, BLC-1 stands as both a cautionary tale and a beacon of hope, a reminder that the universe's greatest answers often lie just beyond the edge of our current understanding, waiting for the right moment to reveal themselves. The Proxima Centauri false alarm might have been a cosmic prank, but it revealed something far more significant: the razor's edge we now walk in the search for extraterrestrial intelligence. BLC-1's brief moment in the spotlight showcased both the incredible precision of modern radio astronomy and its Achilles heel, our own planet's noise. This is where projects like Breakthrough Listen become indispensable. Launched in 2016 with backing from tech billionaire Yuri Milner, this initiative isn't just another SETI program, it's a paradigm shift, combining cutting-edge hardware with machine learning to sift through the universe's static like never before. What sets Breakthrough Listen apart is its scale. While traditional SETI efforts often focused on narrow patches of sky or specific stars, this project casts a galactic-wide net. Its telescopes, from the Green Bank Observatory in West Virginia to the Parkes Dish in Australia, scan millions of frequencies simultaneously, covering 10 times more spectrum than previous searches. But hardware alone isn't enough. The real game changer is how Breakthrough Listen handles data. every hour, its systems generate more information than the entire Library of Congress, and buried in that avalanche could be the faintest whisper of an alien transmission. That's where AI steps in. Machine learning algorithms trained to recognize potential artificial signals filter out the noise, flagging anomalies for human review. It's like having a billion cosmic switchboard operators working around the clock. The Proxima Centauri signal was a perfect test case. When BLC-1 popped up, Breakthrough Listen's rapid response protocol swung into action, coordinating follow-up observations across multiple telescopes within hours. Though the signal turned out to be terrestrial, the speed and precision of the verification process proved something revolutionary. We're no longer stumbling in the dark, hoping to stumble upon a message. We're building a systematic, scientific framework to separate cosmic gold from earthly fool's gold. But the project's ambitions stretch beyond radio waves. Breakthrough Listen also scans for optical laser signals, flashes of light that an advanced civilization might use for interstellar communication. In 2020, the team detected an unusual laser pulse from a distant star, though like BLC-1, it was eventually attributed to human activity. These near misses aren't failures, they're stress tests, refining our ability to distinguish between the universe's natural chatter and something truly extraordinary. Perhaps the most underrated aspect of Breakthrough Listen is its open data philosophy. Unlike earlier SETI efforts, which often kept findings under wraps until verified, this project shares its data publicly, inviting scientists and citizen researchers worldwide to join the hunt. That transparency does more than democratize science, it crowdsources discovery, tapping into collective curiosity to vet potential signals faster than any single team could. The Proxima Centauri signal, for all its anticlimax, underscored a vital truth. The search for extraterrestrial intelligence is no longer the stuff of sci-fi fantasy or haphazard guesswork. It's a rigorous, data-driven endeavor, one that balances optimism with skepticism, wonder with methodology. And as Breakthrough Listen's telescopes keep scanning, as its algorithms grow sharper, we're not just waiting for a message. We're learning how to listen, truly listen, to a universe that may be teeming with voices, each one waiting for the right moment to be heard. Deep within the constellation Scutum, hidden behind veils of interstellar dust, lies a cluster of stars so dense and ancient it defies easy explanation. Glimpse C01 isn't your typical star cluster. Discovered in 2004 by the Spitzer Space Telescope, this tight-knit family of aging stars sits nearly 10,000 light-years away, a relic from the early universe that survived against the odds. But what really makes it stand out isn't just its age, it's the bizarre radio signals emanating from its core, emissions that pulse with a rhythm no natural phenomenon should produce. At first glance, astronomers assumed they were dealing with a garden-variety pulsar, a spinning neutron star beaming radio waves like a cosmic lighthouse. But the signals from Glimpse C01 refused to fit the mold. Unlike the metronomic ticks of ordinary pulsars, these emissions flickered erratically, flaring and fading without pattern. Even stranger, their frequencies drifted in ways that defied the laws of rotating celestial bodies. It was as if something inside the cluster was tuning a radio dial at random, broadcasting bursts of static into the void. Theories erupted. One camp argued for a pulsar nest, a dense swarm of neutron stars packed so tightly their magnetic fields tangled, creating chaotic interference. Others pointed to the cluster's extreme environment, where gravitational forces could warp spacetime enough to distort signals passing through. But the most tantalizing hypothesis: a black widow pulsar, a rare type of neutron star that cannibalizes its companion star, shredding it into a disk of superheated plasma. As material spirals into the pulsar's grasp, it could ignite erratic radio bursts like cosmic Morse code scrambled by the violence of the feast. Yet even these explanations strain to account for the signal's peculiarities. The cluster's advanced age complicates matters. Most pulsars burn out after a few 100 million years, yet glimpse C01 stars are billions of years old. How could such an ancient environment host objects energetic enough to produce these emissions? Some researchers speculate the cluster might harbor a previously unknown class of neutron star, one that siphons energy from dark matter or harnesses quantum phenomena we've yet to describe. Then there's the outlier theory, the one that lingers in the margins of respectable astronomy. Could these signals be artificial? Glimpse C01's density makes it a hypothetical haven for advanced civilizations seeking longevity, a place where stars are so closely packed that interstellar travel would be trivial. If a society built beacons to communicate across such a cluster, their transmissions might resemble the erratic pulses we've detected. It's a notion as speculative as it is thrilling, a reminder that in the absence of definitive answers, even the wildest ideas deserve consideration. What makes Glimpse C01's mystery so compelling isn't just the unknown source of its signals. It's the way this cluster holds up a mirror to our assumptions about how the universe behaves. We expect old stars to fade quietly, yet here they are, shouting into the dark with voices we can't quite decipher. Every new observation peels back another layer, revealing not just the secrets of one strange cluster, but the boundless creativity of the cosmos itself. And until we solve its riddle, Glimpse C01 will keep whispering, or perhaps shouting challenges to everything we think we know. Star clusters like Glimpse C01 aren't just cosmic ornaments, they're bustling interstellar metropolises where the laws of physics get pushed to their limits. Picture a city crammed with skyscrapers, but instead of buildings, imagine stars packed so tightly that a hypothetical resident could travel between solar systems in mere years rather than millennia. This density creates the perfect cauldron for extreme astrophysical phenomena, the kind that might generate signals we've never encountered before. Take pulsars, for example. In a typical galaxy, these spinning neutron stars are lonely beacons, separated by vast stretches of emptiness. But in a globular cluster, they could orbit each other in dizzying proximity, their gravitational dances twisting magnetic fields into knots. When two pulsars collide or exchange material, the resulting energy release could produce radio bursts unlike anything we've catalogued, scrambled, erratic, and defying conventional models. It's the difference between hearing a solo violinist and an entire orchestra tuning at once. The complexity isn't just louder, it's fundamentally different. Then there's the time factor. Most star clusters are ancient, some nearly as old as the universe itself. That means any civilizations forming there would have had billions of years to evolve beyond our wildest imaginings. If advanced societies exist, they might treat these clusters as natural telecommunications hubs, using the dense stellar environment to amplify or relay signals across vast distances. Imagine constructing a network of beacons where stars act as signal boosters, their gravity bending radio waves like lenses. What we perceive as random static could be the overlapping chatter of a galaxy-spanning internet, its protocols utterly alien to us. But here's the twist: these same conditions that make clusters signal-rich also make them fiendishly hard to study. Their dense cores are often obscured by dust, and the sheer volume of stars creates a cacophony of overlapping emissions. It's like trying to eavesdrop on a crowded party from another room. You might catch snippets of conversation, but teasing out individual voices requires tools we're still refining. New techniques like multi-wavelength analysis and AI-driven signal processing are starting to cut through the noise, revealing patterns we once missed. The allure of star clusters isn't just about finding signals, it's about redefining what signals even mean. In these stellar beehives, the universe might be speaking in dialects we've yet to learn. Every erratic pulse from Glimpse C01 or its siblings isn't just a mystery. It's a language lesson from the cosmos, teaching us to listen beyond the predictable rhythms of solitary stars. And if we're patient and maybe a little lucky, we might just catch our first intelligible word. For years, astronomers at Australia's Parkes radio telescope chased ghosts, baffling signals dubbed perytons that seemed to defy all logic. These brief, dispersed bursts of radio waves looked eerily similar to the fast radio bursts arriving from deep space, with one crucial difference: they weren't coming from the cosmos at all. They were coming from the observatory's kitchen. The puzzle began in the late 1990s when Parkes started detecting millisecond-long radio spikes that appeared to originate from the atmosphere. Unlike FRBs, which showed the telltale frequency sweep of interstellar travel, perytons were messier. Their signals scrambled as if they'd bounced off something close by. Researchers initially speculated they might be caused by atmospheric phenomena, lightning interacting with the ionosphere, or even secret military radar tests. But no natural explanation quite fit. Then came the breakthrough, and it was as absurd as it was embarrassing. In 2015, as part of a system upgrade, staff installed a new radio frequency interference monitor at Parkes. The moment it went live, the mystery unraveled. Perytons weren't celestial in origin. They coincided perfectly with one mundane action: opening the microwave oven door mid-cycle. The burst pattern matched exactly, a 2.4 GHz spike leaking from the appliance as its magnetron powered down, the dispersive sweep effect. Caused by the metal telescope structure itself scattering the microwaves, the universe, it turned out, wasn't sending cryptic messages. Hungry astronomers were. The irony was delicious. For nearly 2 decades, scientists had scrutinized these signals for clues to cosmic mysteries, only to discover the culprit was reheated lasagna. But the peryton saga wasn't just a comedy of errors. It was a masterclass in scientific humility. It underscored how even the most sophisticated instruments can be fooled by earthly interference, and how crucial it is to question assumptions. Beyond the humor, the episode had serious implications. Perytons taught astronomers to refine their filters, sharpening their ability to distinguish between human-made noise and genuine cosmic signals. Today, observatories worldwide screen for microwave oven interference as standard practice. The lesson: sometimes the universe's greatest mysteries aren't found in distant galaxies. They're hiding in plain sight right next to the break room coffee machine. Perytons did more than just give astronomers a funny story about microwaves. They rewrote the playbook for how we vet cosmic signals. Before these kitchen-generated ghosts showed up, researchers might have spent months chasing a tantalizing anomaly, only to discover it was human-made interference too late. But today, thanks to that embarrassing revelation, observatories treat every potential signal like a suspect in a cosmic lineup, demanding an airtight alibi before declaring it genuine. The first lesson: local interference can be fiendishly clever. It's not just microwave cell towers, satellite transmissions. Even faulty electronics in telescope facilities have all mimicked extraterrestrial signals at some point. Take the infamous Lorimer Burst, the first recognized fast radio burst. When Duncan Lorimer found it in archived data, skeptics immediately questioned whether it could have been terrestrial. Only after painstakingly ruling out every possible earthly source, from aircraft radar to malfunctioning equipment, did the astronomy community accept its cosmic origin. That rigorous verification process became the gold standard, and it exists partly because of earlier false alarms like perytons, but the deeper insight lies in how we filter signals now. Modern radio telescopes don't just listen to space, they constantly monitor their own surroundings. Breakthrough Listen, for example, uses a network of small antennas near its main dishes to sniff out local interference in real time. If a suspicious signal appears but those peripheral antennas pick it up too, it gets flagged as terrestrial before anyone wastes time chasing it. It's like having a cosmic bouncer at the door, turning away earthly imposters before they crash the party. Perhaps most fascinating is how this scrutiny has reshaped the search for extraterrestrial intelligence itself. SETI researchers now embrace a philosophy called the null hypothesis, starting from the assumption that any signal is probably natural or human-made until proven otherwise. That might sound pessimistic, but it's actually a powerful tool. By forcing themselves to disprove every mundane explanation first, scientists ensure that when they finally do identify a signal as potentially artificial, it'll stand up to the fiercest skepticism. The microwave incident also sparked innovations in signal analysis. Machine learning algorithms now scour telescope data not just for interesting patterns, but for subtle signatures of interference, like the telltale frequency bleed from electronics or the distinct way radio waves scatter off buildings. Some observatories even maintain junk databases of known terrestrial noise sources, automatically filtering them out before astronomers ever see the data. It's cosmic noise-canceling technology, fine-tuned by past mistakes. At its core, the Peryton saga isn't just about microwaves versus aliens. It's a reminder that science advances as much through embarrassment as through triumph. Every time we chase a false signal, we learn how to listen better. Every dead end teaches us where not to look next time. And in a universe where the truth is often stranger than fiction, that ability to tell the cosmic from the kitchen, the profound from the prosaic, might be the most valuable skill of all. Because when the real signal finally comes, we'll be ready, not fooled by ghosts but prepared to recognize something genuinely new. The story of BLC-1 reads like a cosmic detective novel, one where the suspect turns out to be wearing a human-made disguise. In late 2020, as astronomers with the Breakthrough Listen project sifted through data from the Parkes Radio Telescope in Australia, they spotted a needle in the interstellar haystack, a narrowband signal at 982 MHz, drifting ever so slightly in frequency as if tethered to a rotating planet. What set pulses racing wasn't just its artificial-seeming structure, it was the origin point. This signal appeared to emanate from Proxima Centauri, the closest star to our Sun, a mere 4.2 light-years away. Even more tantalizing, that star hosts at least 2 planets, one of which orbits snugly in the so-called habitable zone where liquid water could exist. For a breathless moment, the pieces seemed to align, a signal matching theoretical alien communication markers coming from the nearest conceivable place another civilization might call home. The resemblance to science fiction was uncanny, as if a real-life version of Contact's Vega transmission had arrived. Researchers scrambled to verify their findings, rerunning analyzers to rule out equipment glitches or terrestrial interference. The signal's frequency drift, subtle but measurable, suggested motion consistent with a planet orbiting Proxima Centauri. It wasn't just a blip, it was a candidate. But cracks in the interstellar fantasy soon appeared. When other telescopes trained on Proxima Centauri, they heard nothing. No echo, no repetition, just silence. The signal's frequency, while intriguingly close to what theorists predict an advanced civilization might use, also overlapped with known ranges of human-made electronics. Then came the clincher. Further scrutiny revealed the drift pattern didn't quite match Proxima's expected motion. The final blow landed when researchers traced similar signals to poorly shielded electronics near the observatory. The verdict, BLC-1 was almost certainly a phantom, a whisper of our own technology masquerading as a cosmic hello. Yet the legacy of this near miss extends far beyond disappointment. BLC-1 forced the astronomy community to confront how Earth's electronic noise has muddied the waters of interstellar eavesdropping. In the 1970s, a stray signal might have been dismissed as a curiosity. Today, with satellites, cell towers, and Wi-Fi flooding the radio spectrum, distinguishing a genuine alien transmission from terrestrial static has become a Herculean task. The protocols refined during the BLC-1 investigation, real-time multi-telescope verification, AI-powered interference filtering now set the gold standard for future searches. What makes BLC-1 unforgettable isn't the signal itself, but the questions it leaves echoing. If a faint, human-made blip could trigger such excitement, what might happen when, or if a real signal arrived? The episode underscores both the sophistication of modern SETI and the humility required to practice it. Because in a universe where the line between cosmic revelation and microwave oven interference is perilously thin, the greatest challenge isn't just hearing the universe's signals. It's learning to recognize our own noise well enough to know the difference. From the cryptic blip of the WOW signal to the rhythmic ticking of FRB 180916, these 25 cosmic transmissions have one thing in common: they refuse to fit neatly into any box we build for them. Each signal, whether a fleeting whisper or a repeating enigma, cracks open new questions about the forces shaping our universe. Some, like the Lorimer Burst, remind us how much energy the cosmos can unleash in milliseconds. Others, like Tabby's star's eerie dimming, challenge our very definitions of what's possible. And then there are the false alarms. The Ross 128 incident, BLC-1, teaching us that the line between human noise and cosmic revelation is razor thin. What binds these mysteries together isn't just their strangeness, but their insistence on humility. For every answer we chase magnetars, colliding neutron stars, alien megastructures. The universe tosses us a curveball. FRB 1905-23 shouldn't exist in an aging galaxy, yet there it was. Glimpse C01 signals defy pulsar physics, yet they pulse on. Even the perytons, born from a microwave oven, mocked our certainty. These aren't just puzzles, they're invitations to rethink, to explore, to admit how much we don't know. So where does that leave us? Not at an ending, but at a crossroads. The hunt for these signals has transformed from a fringe pursuit into a cornerstone of modern astronomy, reshaping telescopes, birthing new fields of study, and even redefining how we collaborate across continents. Projects like Breakthrough Listen aren't just scanning the stars, they're building the infrastructure for discoveries we can't yet imagine. And that's the thrill. The next signal could arrive tomorrow or a century from now, carrying answers, or better yet, questions we've never thought to ask. The universe isn't silent. It's a symphony of static bursts and patterns we're only beginning to decode. Whether these whispers come from dying stars, unknowable physics, or something beyond our wildest dreams, they share one undeniable truth: there's so much left to hear. So keep looking up, stay curious, and remember, the next time your phone glitches or the radio crackles, it might not be interference. It might be the cosmos tapping gently on the door, waiting for us to listen just a little harder.